Yeah, this is it visible to all participants?
Yes, sir. This is visible. I think you
ठीक है,
can
ठीक
make
है
it
Nara, thank you.
full screen. You can,
Okay.
so if this can go to full screen mode, it will be bit, it can be better.
Yes, you were saying something.
If this can be made full screen, it can be better, sir.
Yeah, full screen. बढ़ा दे तो
Present,
उसका थोड़ा सा साइड से बढ़ा दो.
presentation mode or
Yeah.
something.
Let's
It's that three dots beside the print option.
हाँ,
I
yeah,
think
yeah, yeah. It's okay. I think
fine. This is fine. This is
yes,
fine.
yes, Ravi. I think it's fine.
Yes, sir.
Thank you, Neeraj. So, good afternoon to all the participants. Uh, they have joined. Ravi, Dr. Ravi.
Yes, sir.
Participants are there.
Yes, sir. There are presently, as of now, there are 15 attendees,
Okay.
participants.
So,
So more would be
ah,
joining.
yeah, no problem. I'll be talking about non-orthogonal multiple access and test and verification also in 5G systems. Okay. So, I mean, all of you are familiar with, at least all the participants are familiar with orthogonal systems that are being used in 2G, 3G, 4G systems. So, like, the very question is why you can say NOMA. I mean, what is the motivation behind you can say uh, having NOMA? And in fact, one very obvious reason is obviously, I mean, with the you can say uh, development of the technology, like in orthogonal systems, we have you can say separate time or frequency slots, and they don't overlap with each other. While in case of NOMA, we look for you can say every user can use at the same time and frequency you can say resources both it can use. Then we are looking for a higher spectral efficiency also, more data rate per hertz, and I mean it also benefits from you can say geographical distribution of users also. The capacity also goes up, and it can serve better cell edge users also, like at the borderline handover problems can be better negotiated in this NOMA systems. And application wise also, like low data rate, I mean like sensor readings, inter-vehicle communication, machine to machine communication, I mean all these can be you can say covered in the I mean through this NOMA. Machine to machine, device to device, internet of things, internet of vehicles, I mean mobile gaming, I mean high energy there are so many you can say applications which we can name them, which we look for I mean in this higher systems. But first of all, briefly I'll uh, talk about multiple access. I think each one of you are familiar, then we can go through them quickly. And the contents, I mean what is a multiple access? I mean if you define, how do you define let's say multiple access? Then multiple access as a technique that lets multiple mobile users share the allocated spectrum in the most effective manner. Now, why this multiple access? Because the spectrum is limited and sharing becomes necessary to improve the overall capacity over a geographical area, more so in mobile users. This is carried out by permitting available bandwidth to be used simultaneously by different users. I think that every probably participant must be familiar having any you can say technical exposure. And in computer networks and telecommunication also, the multiple access methods permit various terminals to connect the same multi-point transmission medium to transmit over it and share its capacity. I think multiple access, I mean, as a tool is has been being used for a long time in all communication systems. Now you can interrupt me also if any participant has any query or question also. So like when we talk about multiple access and we talk about NOMA, I mean NOMA, as we all know, has gradually evolved over, you can say, I mean, this 1G, 2G, 3G, 4G, 5G systems. And in the 5G system, we are uh, talking about, or perhaps thinking, that NOMA can be a better approach in terms of, you can say, users, capacity, spectral efficiency, speed, all those parameters. But first of all, like in case of 1G systems, as you are I mean, frequency division multiple access was used. In fact, this started in the US in 1970s, and later on, I mean, this was the analog system, and later on, in fact, this digital version also came in US, and around 1980s, I mean, European, you can say, I mean, some of the countries, Norwegian, Sweden, or I mean, these people particularly, I mean, these countries or these particular companies working there, they prepared the standard for, you can say, digital, I mean, uh, standards for, you can say, telecommunication or mobile communication, which resulted into what is called GSM, global system of mobile communication. And that uh, standards were so powerful, I think most of the world got connected through GSM. I think within maybe 15-20 years, I think you can see, uh, I mean, in the 2G systems like time division multiplexes, or based on, you can say, 3G systems. Of course, each system had its own merit, demerit, but GSM make, you can say, mobile communication a reality in a true sense by making it visible, or making, perhaps, these are some of the, uh, wireless standardization, like, I mean, how the standardization have gone from, you can say, from blast drive to STC, from 1990s to 2000 to 2010 to 2020. If you look at 2020, then this 5G in the place. So millimeter wave standards we are still, working out. Then quantum averages, then next generation parkways, and H265 standards also. Like for MPG also standards we are thinking, I mean, looking to the many application in 5G systems, like virtual reality, augmented, or I mean, all those uh, associated, you can say, video applications. And before that 5G, we had heterogeneous networks, cognitive radios, software defined networks, and device user, you can say, centric standards, D2D IoT standards. So this particular slide represents like NOMA Parkway also. And I mean, you can see LS, MIMOT, I mean, terraces, this were, so this whole network has evolved. In fact, if you look at, OFDM is very, very, old. Of course, it came into around, you can say, around 2000 only, through this, you can say, 3G systems. But before that, I mean, it was still very old, but I mean, applications only, you can say. Similarly, I mean, in the 1990s also, like blast drives, STC, space-time codes standards, I mean, so many LDC standards, you can say, and the TDM standards, FDM standards. So this particular slide represents a particular standards, and I think all of you probably will appreciate that standard preparation is a very, very, you can say, serious matter. I mean, across the, I mean, you can say, global countries, all, you can say, countries, they try to push of, you can say, their own companies, you can say, standards or perhaps advantages. And that's why this becomes really difficult. Even 5G also, like, not all standards have come up to, you can see, even today. Still they are being working, or you can say it's a very, very tedious, you can say, negotiations that go on. So how 5G is different from 4G? Security, reliability, speed, and uninterrupted signal strength are prime benefits of 5G. Look here, I mean, it's very important. Security, reliability, speed, and uninterrupted signal strength. These are the prime benefits of 5G or 4G. You might say that I mean, some of these points are reliability or this, but 5G systems definitely perform better in terms of all these parameters. Then 5G enabled automation will create unprecedented opportunity in the commercial ecosphere, leading to higher productivity and in turn greater output. Like automation, you can say machine to machine communication, driverless cars, or you can say virtual reality, I mean, augmented, you can say realities. So many applications have recently, you can say, uh, I mean, surface, and 5G system can perhaps only meet out some of the requirements that these kind of, you can say, applications require. Then easy slicing of network, which allows for custom speed, capacity, coverage, encryption, and security management. Like easy slicing means, like suppose we have a, let's say, sensor network. Now you don't need that much of bandwidth or that much of a speed to connect, any sensor network. So that's taken care by this kind of, you can say, NOMA, where, I mean, all, you can say, from very low speed to higher speed, they can be served better. Now, this is a particular slide for 5G network architecture. I think all of you, if you have already been seen it, then applications, I mean, I have prepared this slide in a manner like from the base station to the user, and then the application, if you look at application, then IoT, health, safety, virtual reality, I mean, so many of them, you can say, telco APIs that are already, you can say, being designed or already being operating, in fact, some of them. Then virtualization, that software defined networking controller you have above, you can say, or forwarding, I mean, system. And in case of forwarding system, what is, I mean, being looked into is, you can say, ultra wideband, I mean, millimeter waves, centimeter waves, and then NOMA also, you can say, I mean, how the power domain NOMA, you can say, power multiplexing, where you can see along with the power and frequency, number of users can be accommodated. And if you look at in the small cells, because if you look go for millimeter waves, then the cell size will be obviously, you can say, not that much big. So we will have, you can say, massive MIMO structures, and massive MIMO, along with that, you can say, beam formations. And these beam formation, you can say, number of beam formations that can work out. And then device to device communication also. I think device to device communication is also a very unique feature of 5G systems, where, I mean, the device, one device can communicate with the it doesn't have to go through the, you can say, the base station, or to the, I mean, it doesn't have to route it through the, you can say, that application. So there are some, you can say, protocols being designed where each device can, if it's in, you can say, easily reach of the other device, it can communicate with each other. And others, you can say, in case of this particular layer, a machine to machine communication, IoT based applications, and then in the third one, you can say, cloud RAN, I mean, that architecture front hall, that is a particular architecture for 5G networks, radio access unit. All of you are familiar from circuit switch to packet switching, how we have come over, you can say, across this particular, I mean, with the evolving of this particular kind of mobile communication system. Then what are the application of 5G systems? That 5G based IoT, I think, application, there are a lot many people, I mean, they right now, you can say, talking about IoTs or IoT based applications. Many times, I mean, some students raise the question also, like, why is this IoT become a phenomena, you can say, only in the less recent, like 10, 15 years, you can say, with the coming of, you can say, particularly for after coming of, you can say, 5G. And so one of the reason is because the latency time has reduced, or you can say this generations, like in 5G systems, the latency time has near about, you can say, few milliseconds, which in the 4G systems was obviously around 20, 25 milliseconds, you can say. And so with the decreasing of this latency time, you can respond better to any kind of, you can say, whether it's a I mean your you can say production floor, or you can say your any kind of you want to raise the production or you want to reduce the production, any kind of instructions you can pass on, you can say in milliseconds. And so from remotely also you can control any these kind of systems. I mean, there are, I think, a number of applications which has been already talked about IoT based. This is a very important part of this 5G system. Then mobile networking and telecommunications, AI enabled robots. That's what we every day we listen to on our TVs also and newspaper also, like what this artificial intelligence is going to do. Lot many you can say applications people are talking. Lot many applications are we can see every day in I mean social media or other way, like what artificial intelligence can do. And industry is still you can say promising a lot in fact, and they are potentially lot of forecast you can say that the routine jobs can be taken care by artificial intelligence based systems. But definitely it's a new technology, and how does it save probably that has to be seen. Medical appliances, that is another applications you can say, whether it's I mean health monitoring systems, or you can say telemedicine, or all applications like in medical appliances also. I mean this kind of applications are getting their at least applications, or perhaps being used. Smart homes, defense. I mean, if you look at in the defense systems also, like whether it's a drone technology or other kind of you can say our fighter planes or controls, or uh, all kind of you can say communications are being used to obviously strengthen the our counter offensive you can say systems, and you can say attack systems also, where I mean we can secure the sky you can say, or our installations. Aerospace is another applications you can say for 5G systems. Self-driven vehicles, I mean, uh, of course, still not we can I mean maybe in America, or you can say systems where there are some regulated traffics you can say, or uh, people follow certain rules, like these kind of vehicles are being tested by as a pilot project. Of course still there are I mean very few cases where the self-driven vehicles have really you can say promise a very you can say potentially very high order application, but still they are you can say very well tested, and probably it will take much more you can say time in our country at least to look for you can say self-driven vehicles or driverless cars. Then the autonomous industrial equipment also, 5G systems, as I said, based on IoT or based on many of other aspects. This, I mean, equipment can be remotely also, you can say, controlled remotely, be inventories or all kind of, supply chain management issues. They can be looked into or can be perhaps served also very well by agriculture machinery, augmented reality. So many applications. I think these are only few. I have this frequency division multiple access. I think each one of you know that frequency and power issue. You can divide this particular slots. I mean, some of the advantages are. I mean, if you look at the advantages are it lowers the intersymbol interference, equalization. Okay, simple to implement from a hardware. In fact, frequency division multiple access came because of you can if you look at satellite communication. Satellite communication started with frequency division multiple access in the beginning. That also analog part, like you had some filters, and those filters where you could separate the particular you can say particular frequency and particular application also that could be linked with a particular transponder. So that served also over a time, but obviously it has some certain disadvantage also, like it's suitable only for analog signals. The storage enhancement of signal is not possible. Large bandwidth requirement for transponders. Guard bands may obviously waste some capacity. It requires RF filters to meet stringent adjacent channel rejection specifications. Now, this may increase the cost of the system because you have to keep it. The system is very robust, at least to, and in particularly in satellite communication or any wireless communication system, you can say, I mean, the kind of signal to noise ratio, that stringent power requirements, that obviously it reduces certain limitations. So uh, to reject, this kind of, you can say, channel interferences, or that becomes a difficult job. Network planning is cumbersome and time critical. Frequency planning is more time consuming, required multi-channel receivers that are expensive. I mean, every, you can say, application or every transponder, you have to separate, design a particular receiver, and the receiver obviously looking to the power levels that are operative. I mean, you have to design the corresponding low noise amplifiers and the transceivers, and then again to detect all that particular signals is obviously a cumbersome process. The highest bit rate per channel is fixed also in this. So some of these advantage. Then time division multiplexes is a, you can say, we divide into the number of, you can say, time slots corresponding to some frequency. Now advantages, I mean, the TDMA can, you can say, convey, I mean, 64 kbps to 120 mbps information rates. Of course, it depends upon your bandwidth also. I mean, how much of the bandwidth is, you can say, you are trying to use for particular, I mean, this slot, you can say, demarcations. Then it offers a solitary transporter recurrence with different clients. Okay, I mean, each client can have a dedicated line, you can say, particularly in this system. No need for an exact narrowband channel. TDMA isolates clients as per time guarantees that there will be no obstruction from the concurrent transmission. Normally, no interference comes. Of course, I mean, there will be some cases where we do listen, so some co-channel interference issues may be there, but normally you can remove them, and the systems are very robust. TDMA offers significant investment funds in base station hardware. Space and support is significant factor, and cell size becomes ever more modest. In fact, over the years, this technology, TDMA, has almost, you can say, stabilized across the world, and for a long time it is being, for the last, I mean, 50, 60 years, this technology is being widely used, you can say, all across the world. Some of the disadvantages, it's exposed to multipath twisting. Organization and range arranging is concentrated. High synchronization overheads, recurrence, opening assignment is to be intricate in TDMA. Okay, so you have to really, you can say, have some uh, bits per particular synchronization or particular access, you can say, bits you have to transmit to just for synchronization or for, you can say, end of a message or particular channel, particular frame. And so that it consumes, you can say, more number of bits are required, at least in addition to your message. Then signal processing, that is again obviously signal processing requirements, you can say, add up to the resources, and those kind of, you can say, systems. If you look at even the 5G systems, I'll talk later on, like signal processing, the beam formation at the back end on the base stations, that required, you can say, very fast responses. And because coming of this technology, you can say, we do have, you can say, those kind of signal processing capabilities, signal processors who could, process this kind of enormous amount of information, and uh, provide us the kind of, you can say, support in this beam formation. This next one is code division multiple access. This code division multiple access, where many transmitters can send information simultaneously over a single communication channel. This is a US based, I mean, Qualcomm, the company that, you can say, commercialize this particular. And I think CDMA has its origin in, again, in the defense applications first, because they wanted to have secure communication. The biggest merit of CDMA is it can have, very secure communication. Besides, you can say, I mean, for networking purposes also, this was in the 3G systems, this was used for this particular mobile communication, mobile networking cases also. So this allows, I mean, many users to share a band of frequencies, I mean, the bandwidth and the channel across time and frequency through some code To permit this without undue interference between the users, CDMA employs a speed spectrum technology and a special coding scheme. That coding obviously is very, you can say, large code, Walls code, or I mean that normally the kind of block codes which have a bit length of near about, you can say, 63 bits. So if you look at theoretically, I mean 2 to the power 63 uh, codes can be generated. I mean, looking to the bit length of the code, but it's very difficult. And particularly if you look at the kind of its communication applications or this thing, uh, getting this kind of orthogonal codes becomes almost impossible. And that's why uh, you can say, I mean, this kind of system where we can think about serving 2 to the power 63 people at a time, that becomes a unrealistic, you can say, proposition. But all the same, I mean, if you can generate more orthogonal codes, obviously more. And that's why the capacity of the CDMA system is also higher than TDMA systems. CDMA optimizes the use of available, and the if you look at the power level also, CDMA can operate at a lower level, you can say, power level. This optimizes the use of available bandwidth as it transmits over the entire frequency range and does not limit the user's frequency range. So that means the whole spectrum is available to every user. IS-95, also called CDMA1, and its 3G evolution CDMA 2000 are often simply referred as CDMA, but UMTS 3G standards used by GSM carriers also uses wideband CDMA as well as TD CDMA and TD SC DMA as its radio technologies, and it's being widely used. In fact, these kind of systems are still in application. So it doesn't need the kind of synchronization that we look into time. TDMA, it has better multipath execution, and it has multiple times limit than the GSM. Obviously, 4 times, you can say, and the capacity also. And then through rake receiver or others, we can negotiate, multipath or fading also. So that advantage also can be with this code division multiple access technology. The disadvantage is this the kind of time synchronization that is in the, I mean, if it's a high speed network, some synchronization is necessary. It cannot offer international roaming, a large GSM advantage. The CDMA system performance degrades with an increase in the number of users because the multi-access interference will increase. And so the signal ratio that you have to provide to each user with its signal, that can be hardly maintained. And that's why you can say maybe some call drop will be there, or I mean the user satisfaction with the kind of service will be obviously not good if the number of users become more than uh, that you can say a minimum signal to noise ratio based service has to be provided to every user. And while we are using CDMA, code length can be carefully selected because it can induce delays also. Like obviously processing, as I said, the kind of code that were secure enough, obviously large code lengths, and so like it can also delay the processing, and then it does suffer from self jamming problem. Now then comes the orthogonal multiple access, and in OFDM, multiply closed space orthogonal subcarrier signals with overlapping spectra are transmitted. That's what the 4G systems we has been used. And now demodulation is based on fast Fourier transform algorithms. If you look at this particular slide, we have the subcarrier peaks. That means uh, the carriers are, I mean, each one of, you can say, carry frequency that is carrying information, whether depends upon how you map your information with this kind of carriers, but they're orthogonally space overlapping subcarrier. Now the question is, if they are overlapping, whether it's advantageous or disadvantageous. In, I mean, it can be disadvantageous also. It can be the advantage, of course, is obviously they are orthogonal, but disadvantage can be like if they are overlapping, their peak average, I mean the power ratio, that can be very high because if they are overlapping, then the peak average ratio that particularly each subcarrier will have, you can say, with this overlapping carrier. And then the kind of device we have, the device find it difficult to, because obviously if it's a higher power, then obviously there will be more heating. More heating means, I mean, obviously the chips or the other systems that you implement upon, they will obviously have some problem, or you can say we have to really take care of those kind of, you can say, problems. And the advantage can be, if you look at this kind of 4G systems which have served very well. In fact, the capacity is almost, they're promising 1 GB, but if it's not, at least, I mean, all of us are now having our video calls, or you can say uh, all many other applications are being very comfortably, you can say, uh, accessible to all the users. And another, in fact, if you have studied a little bit about wireless communication, then the channel fading can be negotiated. Channel fading, particularly a frequency selective fading. Now, advantage of FDM is it converts this frequency selective fading into some flat fading. So that means, I mean, no signal of any frequency will getting, you can say, getting eliminated, or getting, you can say, disappearing. Rather than, I mean, that signal can be retrieved also easily, even if it's a, you can say, this kind of fading is, you can say, comes across this kind of signal transmission. So many advantage. And now this, they are closely spaced subcarrier, and the subcarrier nulls correspond to peaks of adjacent subcarrier, zero intercarrier interference, and these are the sync function lobes that is with, along with that. But of course, LTE systems that are right now, you can say, in operating in 4G system, they are using OFDM as a, you can say, you can say, as a modulation scheme, or as a, you can say, access scheme for implementing these services. Now, what are the advantages of orthogonal? As I told a little bit of efficient use of the spectrum by allowing overlap, eliminates ISI and IFI through use of a cyclic prefix. Okay, so that means, I mean, we provide where the, you can say, the frame is starting, so we provide certain, you can say, one or two parity bits, you can call them, so that it can be easily made out that where the message is starting, or at least if there is some delays or some, that bit can take care of, or for synchronization also it can help us. Simple channel equalization. Channel equalization, why do we need channel equalization? Because there will be some, you can say, delays across the channel propagation, and to get over to, you can say, this kind of, channel distortions or channel delays, we normally use channel equalizer. Not only, you can say, the wireless only, even the wired media also, like coaxial cable or this thing, we normally use those kind of, channel equalization. Because if you look at, transmission, if you try you what you transmit, you transmit a binary pulse. If you transmit a binary pulse, and 0 1, I mean, if you look at its, uh, frequency domain is spectrum, then obviously this is almost infinite. So you have to do little bit of, pulse shaping also, what kind of pulse which will consuming less bandwidth, and then those kind of pulse can be supported on the channel. But in OFDM also, this channel equalization is necessary looking to the channel conditions. OFDM is computationally efficient by using FFT technique to implement modulation and demodulation. I mean, we can implement it fast Fourier transform. This provides good protection against co-channel interference and impulsive parasitic noise. This is another advantage. The disadvantage is RF power amplifier with high peak to average power ratio. That's what I talked about. I mean, the peak to average power ratio is uh, operative, and so these amplifier find, because if for any amplifier also, if they operate at a high, power level, obviously they will go in non-linear regions, and non-linear regions means some harmonics or some other introduction, and obviously that will lead to some other problem as far as the signal transmission is concerned. It's more sensitive to carrier frequency offset and drift than single carrier system due to leakage of the DFT. That's another, you can say, the kind of frequency offset. Now come the non-orthogonal multiple access. Now we have so far talked about some of these merits of these orthogonal systems now, but our main topic here is non-orthogonal NOMA. The traditional orthogonal multiple access technique, only one user can be served in each time frequency resource. That's what I mean, resource block. This drawback limits the applicability of these access techniques in the 5G and beyond era, which require massive connectivity, high spectrum energy efficiency, large throughput, and low latency. So, I mean, if you the kind of as I talked earlier on, with this coming of this 5G technology, I mean, you need massive connectivity, you need a very high spectrum energy efficiency to increase the speed, also to increase the, like you can say, your latency time, also to reduce the latency time. And for that purpose, I mean, this 5G systems, they will have to be obviously different than, or perhaps better than, what are existing systems. As an alternative, non-orthogonal multiple access has become a promising solution to overcome the limitation of OM. Now, what is the limitation? That also I'll talk about OM orthogonal systems. Since it provides additional degree of freedom from non-orthogonal resource utilization in either the power domain or code domain, I'll talk about, discuss that later on. This domain extends the dimensionality of the resource block so that multiple users can be served in the same resource block. However, this unique arrangement results in several challenges for the design of NOMA systems. Obviously, this technology is still even not fully, you can say, operative. If you look at the non-orthogonal multiple access, now the channel capacity. Now, the first question may be, how does this NOMA improves the speed? Like 1 GB, we are promising 10 GB in 5G systems. So you can see from the graph, I mean, rate of one user to two user. If you look at the red, this particular dotted lines, that is corresponding to orthogonal multiple access. But if you look at the NOMA, non-orthogonal, the speed can be higher than what is orthogonal. Okay, and it can be proved also, like this more clear in the second, you can say, this B figure, where this orthogonal is almost, you can say, linear, while NOMA, you can say, is at the higher order, or the rate of speed can be very high. In fact, if you look at the, if you compare orthogonal or non-orthogonal, and if you plot, you can say, on x-axis the speed that can be achieved through, you can say, OMA, or through, you can say, this particular NOMA. I mean, if you look at that, the speed can be almost 100% or 200% more than what it can be achieved through OMA. So like it can go up to, I mean, 8 Gbps. If you plot, you can see corresponding to, I mean, if you plot on y-axis CDF, and the throughput for OMA and NOMA for number of users 2 or 3, then the users, you can say, download speed can go up to almost 7-8 GB in comparison to, you can say, almost 3 to 4 GB in case of orthogonal systems. So this particular graph displays that NOMA is more efficient, more, you can say, useful technology to increase the, you can say, speed of the system. That's a theoretically, and because you can prove it through, Shannon channel also. Like there are two users, if you allocate them W/2 bandwidth, W/2 bandwidth, and then if you combine them, if you put them through orthogonal, or if you put through them NOMA, because in NOMA whole of the bandwidth is being used by all, you can say, users. So if there also you can prove that this NOMA will perform better than the orthogonal. Now, what are the typical, you can say, type of NOMA? They are broadly classified into two categories: power domain multiplexing and code domain multiplexing. What is, based on power multiplexing? That's also, I think, very easy to understand. Now, if you look at an OFDMA system in this particular slide, then you have user 1 and you have user 2. Both of them are utilizing and allocated separate bandwidths. On x-axis is the frequency. So each user is having a particular, you can say, frequency spectrum allocated. Now, if you look at the NOMA, I mean, whole of the frequency is being, shared by two users. The top one, I mean, is having, you can say, I mean, shown a little bit of, you can say, with the small amplitude, and the lower one with the, higher amplitude, but both the users are having, you can say, same frequency. And as I talked earlier on, they are sharing this resources. So what happens in power multiplexing, like, uh, I mean, i'm having I'm basically I'm giving more power to the far user than the base station. A user which is far off from the base station will get more power, obviously. And if a user is near the base station, I'll give him lower power. That's quite obvious. I think all of you know from CDMA systems also, like near far problems, or you can say this kind of power management is already, I think, is known to probably students who have done particularly the BTech course on mobile, or studied some course on mobile. So, like, I mean, more power is given. So, I mean, the base station, you can say, is handling both the users. One user, it is giving, you can say, more power. Another, in case of power multiplexing. Now look at here. Uh, in case of how does it happen, you can say how the users are getting, this particular getting recovering their signal. So if user 1 to user m, if you in this graph, if you look at power multiplexing, and the power that we plotting on the y-axis, so user 1, user 2, they are getting different power level. And of course the third dimension is the time. And the base station, if you look at this particular graph, the base station, that is, you can say, superposing, imposing all the solutions or all the signals also together, being sent by the user. So what it does is, you can say it allocates, you can say, I mean, if you have user m and user n, and I mean user m and user n, I mean, you can say different. So what, let us say the user m is far off and the user n is nearby. So in case of power multiplexing, this user m will first, you can say, subtract the user m signal. That means, I mean, you can say, a particular user, it will obviously remove the interference. Obviously it is an interference for it, for the whatever the signal user m is having. And that one of the technique that is used is what is called serial interference cancellation, SIC, that is shown in the graph also. Like, there is a serial, I mean, these are the techniques. I mean, you can have, parallel interference cancellers also. We can have many other, techniques where we can reduce the interference. But in this power multiplexing, what we use is this particular, you can say, serial interference canceller. And I remove that particular am user signal from my signal, and then I recover my detection through, I mean, the you can say my own detection mechanism. Now for the user m, if it is really far off, the power level corresponding of the, you can say, user n, that of course it will be receiving, but the user power level will be so low that it doesn't interfere with, you can say, user m signal. So normally we don't, it will be at a particular power level where you don't have to even bother about it, or it will not be interfering with, you can say. So it can decode it, uh, I mean, you can say, straightforward. I mean, it does not have to process it. Now this is only for two user. If it's more than two user, obviously you'll have to do work out that. If it's, you can say, three users or four users, then the user two, where their locations are, so obviously they will have to carry out this, you can say, process or this particular mechanism repeatedly also. Like, first they will remove the highest, you can say, interference, and then the next one and the next one. By the time they get their own, you can say, corresponding signal. So I think you understand. Now this is again this particular, I mean, uplink normal transmission, that is in the downlink normal transmission. In case of uplink also, the base stations, I mean, both the users will be uplinking with different power levels. And the serial interference cancellation, you can see, corresponding to the uplink also, and user m detection, that is done. I think it's clear. Yes, any question? Now this was the downlink norma transmission. Now superposition coding SC at the transmitter, successive interference cancellation at the receiver. In fact, you will be, perhaps you can understand or realize also, like, a tablet PC or our mobile have now as much computation power as, you can say, a laptop had. Now they are almost a computation power of a laptop near about. So I mean, this kind of calculation could not be, carried out in, you can say, around 10 year or 20 year back. But now this particular mobile communication are also equipped with such a, processing part, so that they can easily carry out this particular, serial interference cancellations or parallel interference cancellation. And we can implement those kind of, you can say, this particular processes on our, you can see, this mobile handsets. So that's again, it's because of the technology, you can say, evolution that it has become. Now this is what we have discussed for the, I mean, power multiplexing for uplink also. In case of uplink also, it can be. So multiple users transmit their own uplink signal to base station in the same resource block. The base station detects all the messages of the users with the aid of SIC. I mean, obviously the base station always have this serial difference cancellers. The basic form of NOMA with SIC exploit SINI difference among users, either due to the natural near far effect or by non-uniform power allocation at the transmitter. So the base station is also differentiating, you can say, different users based upon their power, you can say, allocation. Now this is what next, problem, you can say, NOMA in massive MIMO system. There are a lot of talk about massive MIMO, and there's a lot of understanding about also what is happening in this MIMO. I mean, are we transmitting different signals in the different time slots, or you can say there is a lot of redundancy there. It's really, and then why we are this massive, you can say, more than one antenna will ensure and ensures more capacity, or in what way does it, but that's because of, you can say, inherent nature of the wireless, environment, where the channel fading is a very, very, you can say, challenging task. And these MIMO systems, they help us into ensuring reliability. That means the signal will be reaching more reliable with the MIMO system, because especially if you look at, their positioning, they are obviously separated in space also, and in time also you can separate them. So, and that means the multipath propagation or other things that really distort the signal, that obviously if you have more, you can see, this kind of signals reaching to the receiver, then that can be negotiated better. So if you look at here, I mean, this is one of the most important part of the 5G implementation, and this is the most critical part. In fact, this the success of this technology depends upon in this beam generation. Like each user is given a particular beam. I mean, as we are talking about the capacity, what is the capacity? Capacity is about, uh, I mean, they are promising lakhs of, you can say, connective devices with one base station. Now lakhs of the devices, like your microwave oven will be also connected, your car will be also connected, your, you can say, every appliances in your house, your mobile or your other TV or anything, they are all connected with the base station. So I mean, how the base station can serve them, so many of them to simultaneously, and that is only through, you can say, having this, uh, you can say, beam formation. And what we have so far talked about is, we have talked about, you can say, time multiplexing or time, uh, you can say, we separate the signal across time, and you can say frequency. But in case of beam formation, it is a spatial multiplexing, you can call it, because the same frequency can be used to serve two user, uh, by orienting one beam in a one direction, another beam in the other direction. One beam is not interfering with the other. So how is this beam formation technology? That's again, of course, being used in defense at number of applications, whether radar or, you can say, our, all these, you can say, moving objects in the space. So this particular, the basic or method of, uh, realizing this particular beam is, you can say, changing the weight gate values, changing the weight factors at the feed networks. That means, as you know about, I think, array structures in antennas. Now arrays means more than one element. Obviously they increase the gain. They many other features, you can say, you can reduce the beam width also. So those kind of, you can say, arrays, uh, which particular, you can say, arrays you will excite, or you can say you will feed on, and they will be, you can say, generating a particular beam, or you can say uh, f- which will be directed in one direction, because all the field, you can say, that they will be adding up in a particular direction as per our control. And as I talked earlier on, like signal processor base, I mean, you can say, quickly, I mean, this beam has to serve. If suppose a user is moving, this beam will be, obviously will have to move on. So how does it move? At the back end, you have to have keep on getting the feedback that this user is moving, and if the user is moving, the beam has to also shift on. How does the beam shift? The beam shifts only when there are, you can say, these weight factors. They are changed at the base station, and the base station change means some back end signal processors. They help us into identifying the corresponding weights, and then quickly implementing, you can say, quickly supplying it to the base station, so that the beam formation, or this user can be connected with the same, you can say, user. And like, this is how you can see this particular beam. And this is the most challenging part of the, you can say, implementation of 5G system that is coming up, and a lot of companies are still working on these solutions. Now, this is massive MIMO systems. NOMA can be used in conjunction with multi-user, multiple input, multiple output, to further improve the system spectral efficiency. Multiple transmit antennas at base station are used to form different beams in a spatial domain. I think you should understand this. Is spatial domain means, I mean, the space, I mean, the same frequency signal, like the basic mobile communication systems. I mean, we use, like our, when, how do we do the frequency planning? Like, you can see you have the cell. I mean, the same frequency can be used after certain 2n plus 4, or I mean, the cell. Here, I mean, you can use the same frequency. If you can identify, you can generate a particular, you can say, this beam, which doesn't interfere with the other user. The same frequency can serve both of them. Maybe one you can say user at seventh floor, another can be at the ground floor, if the beam is really sharp enough, so they don't interfere, and that obviously will increase the capacity of the system. At the receiver, the interbeam interference can be suppressed by spatial multi filtering. Intra-beam SIC can be used to remove the inter-user interference. Now, these are obviously some helping, you can say, this particular. The extension of NOMA in massive MIMO system can further improve spectral efficiency. NOMA based on power multiplexing, this is what I mean again. Now, these are the user pair 1 or 2, and this is the cell 1, and you can see this is the cell 2. So, how that are again shown as how the two user will be using. Now, when transmit power allocation is biased towards faraway users in downlink NOMA cell, edge users experience increased interference from neighboring cells. In a two-user NOMA scheme, user 1 and user 2 are served by base 1, while user 3 are served by base 2. A strong interference is expected between users 1 and 3, which may degrade the performance. These are some of the limitations of, you can say, NOMA. NOMA based on power multiplexing. To mitigate the intercell interference, joint pre-coding of NOMA user signals across neighboring cells can be considered. So you can do some, I mean, some other technique of reducing this interference, joint pre-coding. This requires that all users' data and CSI, channel state information, should be available at multiple base stations. But finding the optimal precoder, I mean, it's not such a, you can say, easy solution. Moreover, the multi-user precoding used for the single cell NOMA may not be feasible for the network NOMA scenario, since the precoder for geographically separate base station does not actually form the physical beam that can readily be used for intra-beam NOMA. I mean, some of the, you can say, more finer details of this beam formation, based on the fact that large scale feeding would be quite different between the links to different cells. A complexity reduced precoding scheme for network NOMA has been proposed, in which multi-cell joint precoder is applied only to cell edge users. So this is again a selective solutions across the handover problem. Now, the next you can say NOMA technique is based on code domain multiplexing. So what do we do in code domain multiplexing? We do use what is called low density spreading, CDMA also you can call it, this kind of technique. And if you look at this technique, The orthogonal frequency division multiplexing can be considered as a combined version of LDS, CDMA, and OFDM. In LDS OFDM, the transmitted symbols are first mapped to certain LDS sequences and then transmitted on different OFDM carriers. So, like you have the encoders, and then you map the signal to some, you can say, frequency, and that is transmitted across the, you can say, free space. The number of symbols can be greater than the number of subcarriers. That is, overcrowding is allowed to improve spectral efficiency. That means, sometimes you can say more than one message might be, you can say, loaded on a particular carrier. Now this is norma based on code domain multiplexing. What happens in the code domain multiplexing? I mean, you can say sparse code words. Now, so you have bit streams which are mapped to sparse code words. That means each user will have a code word. Okay, so this is the code book. Now, this code book, we have 6 sparse code words. They are transmitted over 4 orthogonal resources. So, like 1, 2, 3, 4, 5, 6, like you can say, we have sparse code words, code book. And this code book, that depends upon, the number of at least code books that perhaps we can design on, that depends upon our design ingenuity. And each user, you can say, this particular 6 sparse code word, they will be transmitted across these 4 orthogonal resources, and they are in terms of, you can say, MUD based on this particular you can say code technique. Now, sparse code multiple access, as I on the above slide we have talked about. Now this sparse code multiple access is, this is enhanced version of the LDS CDMA. Unlike LDS CDMA, SCMA directly maps different bit stream to different sparse code words. What is meaning of sparse code words is basically you want to make sure, or how do you can say differentiate the two signals. So in the first part we differentiated them based on power. Now in this case we are trying to differentiate two signals through some code, two or more than two. We can have more than you can say users also. Each user has a predefined code book. All code words in the same code book contain zeros in the same two dimension, and the positions of zeros in different code words are distinct to facilitate the collision. These particular zeros are, not at the same location as at the, you can say, for the these particular code words. For each user, 2 bits are mapped to a complex code word. 2 bits are taken for each user, and then they will be mapped through their code word to, you can say, corresponding to final encoder output. Code words for all users are multiplexed over 4 shared orthogonal resources, FDM subcarrier. The key difference between LDS CDMA and SCMA is that multidimensional constellation for SCMA is designed to generate code books. That's very important. Okay. Multidimensional constellation. What is meaning of constellation? I think all of you know about, when we talk about digital receivers, we talk about signal space representation. Constellation, QPSK, MRAPSK, now QSK or QAM, or those kind of BPSK, BFSK, you can say AMA, you can say minimum shift keying, MSK. These all these are the different examples of, you can say, modulation. So this, in this constellation diagram is, you can call it signal space diagram. That means what are the signals you are using to transmit their almost, you can say, geometrical representation on the particular, you can say, two-dimensional structure. I hope you understand it. Multidimensional constellation. So multidimensional constellation means, the constellation diagram itself can change. In fact, you will see that the shape gain is also provided in case of, you can see, this particular code domain multiplexing. And this is designed to generate code books which bring the shaping gain. What is shaping gain means? Shaping gain comes through constellation change in the constellation. Now, if you look at, QPSK itself, now the QPSK for user and user 2, you can always design in a manner that your QPSK particular one message you change over. You can say far user or near user, you can separately assign a particular bit nearby that. The shaping gain is the gain in the average symbol energy when the shape of the constellation is changed. The constellation shape is changed, and that gives me certain gain that will steady. uh, More about, I think, in some other probably lecture. This is part called multiple axis. In general, shaping gain is higher when the shape of the constellation is closer to a sphere, and the maximum achievable shaping gain by the optimization of a multidimensional constellation is 1.53 dB. Those of you who have studied, this digital communication, you must have seen that. Like when we prepared the diagram for QPSK, it's almost all there. Four are on a radius. I mean, you can say on a sphere. And similarly, I mean, many other, you can say, we can prepare those. So this particular is just closer to a sphere, and when they give the maximum achievable shaping gain. For the concatenated approach in high modulation order, the multidimensional constellation can be optimized to obtain shaping gain, and then code books are generated based on the multidimensional constellation. In SCMA codebook, design is complicated problem since different layers are multiplexed with different code books. As the appropriate design criteria and specific solution to multidimensional problem are still unknown, the multi-stage approach has been proposed to realize a suboptimal solution. So there is not any exact solution. I mean, each one of them, you can say, are exploring some solution that maybe this can work better. Now, if you look at specifically n-dimensional complex constellation with m points, I don't have the board otherwise, which is called the mother constellation, is first optimized to improve the shaping gain, and then some code book specific operations are performed of the mother constellation to generate n-dimensional constellation for each code book. That means each code user will have a different constellation, and that's where from the shaping gain is coming up. The constellation itself can be oriented in a manner so that it gives me some added advantage. I mean, 1.5 GB, 1.5 dB gain, it may appear to be, but any kind of, in wireless propagation, 1 GB or 2 dB, I mean, every, you can say, uh, gain, that's really very, very, you can say, welcome. Obviously, you can say, by any user or by any company or by any designer, they obviously look for, I mean, any kind of, you can say, advantage with it. And particularly now in a global, you can say, global warming or other issues, each you can say technology, I mean, you can say, companies or particular designers are also emphasizing that the power should be consumed as small as possible to make this happen. And there, this kind of, solutions become far more, if you can reduce the power consumption by 1 dB or 2 dB, that's an enormous advantage. If you look at the number of users of this, you can say, applications, it's enormous. So, but anyway, constellation, if the constellation is changing, the constellation provides me some gain. Three typical operations are phase rotation, complex conjugate, and dimensional permutation of the constellation. So that's very simple. Phase rotation is very simple to understand. Then we can do a complex conjugate operation or dimensional permutation. In the generated n-dimensional constellation after codebook specific operations, each n-dimensional constellation point is multiplied with a projectional matrix to generate k-dimensional code word, which has n non-zero element from the component of n-dimensional constellation point. In this way, codebook with m code words can be obtained. That's one process that has been worked out. Now, if you look at NOMA based on code domain multiplexing, each user symbol are spread by a specifically designed sequence. You can see here user one, there is a spreading here, and then corresponding to the, you can see, corresponding to, they are through certain code, these spread symbols are transmitted on same orthogonal resources, user one, user two to user m. This code division in the uplink, this particular system, symbol of each user are spread by spreading sequence. Multiple spreading sequences constitute a pool which each user can randomly pick one of the sequences. Then all spreading symbols are transmitted over the same time frequency resources. The spreading sequence should have low cross correlation and can be m array. At the receiver, code word level SIC used to separate data from different users. So again, it says SIC, that is being like in the power multiplexing, SIC is being used in the code also to distinguish between two code words. The complexity of code word level SIC is less of an issue in the uplink, as in case of receiver needs to decode the data for all users. Now, the downlink users are separated into K groups. Each group, different user symbols are mapped to different constellation that can ensure gray mapping of the combined constellation. The combined constellation is determined not only by the modulation order of each user but also by the transmit power partition among multiplex users. Orthogonal sequence can be used to spread the superposed symbols to get time and frequency diversity gain. Now, the gray mapping, all of you know about. I think if you look at 2-bit gray mapping, we use this gray, you can say, mapping in number of other applications also to use it. So, in conclusion, NOMA eliminates the limitation of conventional orthogonal multiple access technique where only a single user can be served in each user. It improves the efficiency of the system. Compared to conventional OMA, NOMA allows controllable interference to realize overloading of the cost of tolerable increase of receive complexity. Therefore, the demand for spectral efficiency and massive connectivity for 5G can be partially fulfilled by the NOMA. It is expected that NOMA will play an important role in the future all wireless applications. Along with 5G, in fact, I wanted to devote some time to this test and instruments also, like as a you can say as a participant. If you look at the 5G systems, like in those who are familiar with chip design or chip, because when you fabricate chip, you test it. So how do you test? I mean, there are test processes. There are some test processes which are inbuilt in the chip itself, so that whenever the chip is fabricated, we can use those kind of, you can say, routes to make out that our at a particular node the voltage is correct, at the particular node the current is okay. Okay, so this testing is done. Now the same, if you can say extend this logic to high frequency this instruments, like in case of 5G communication, the 5G communication spectrum, if you look at right now, which is working in sub 6 gigahertz band. So sub 6 band, I mean, you have already some lectures, I think, from that corresponding to some 3.6 to some, I mean, in this below sub 6 gigahertz. And then you have the particular bands allocated from, I mean, between 10 to 20 gigahertz also, and 20 to 30 gigahertz, up to 50, 60 gigahertz, that bandwidth allocations have been made for 5G communication. So if you are operating, let's say, at 20 gigahertz or 30 gigahertz, I mean, thinking about, you can say, making the instrument, how do you test them? Because when you design a system, I mean, can you design a VLSI chip, let's say, for 20 gigahertz signal, or it can be operative to that? Obviously, it will not work out. So you will have to go to some millimeter wave integrated circuits. Okay, and that means those who are familiar with the MICs, microwave integrated circuits, so high frequency, this kind of devices, you will have to go to some new technologies. Not only that, if how do you test them? We do not have that kind of, you can say, possibility as we have in VLSI. So that means once you design, once you fabricate, then only you can test it. And if during the testing, if something goes wrong, what happens? Again, you have to go back, and that obviously is very costly. So this test and instrument part of the 5G communication, particularly for electronics and communication student, can be really very good opportunity, because in future this kind of, you can say, high frequency uh, appliances, or high frequency, you can say, these particular instruments, they will require a kind of, you can say, manpower which can take care of them. And that's one of the challenge. These are some of my references I use. I mean, you can note down it, or you can see that this is Bocardi et al. 5 Disruptive Technology Directions for 5G IEEE Communication Magazine, that came into February 2014. Non-orthogonal multiple access for future radio, that is a proceeding of IEEE VTC Spring, that's June 2030. Then non-orthogonal access with random beam forming and intra-beam SiC for cellular MIMO downlink. That is in again IEEE 2013. Of course, the ideas kept on coming up, but still in the, at least if you look at the particular operational level, I mean, all companies are really working hard or struggling hard to really realize some of this potential of this the technology. Okay, so I have finished my presentation. Now, if any question you have, I can answer that. Ravi, hello, Ravi. This is my question. I should my mute.